Today we're going to continue our exploration of multivariable calculus. So in previous videos we've looked at partial derivatives. We've also looked at how to sketch functions of two variables and the surfaces associated with them. And we've also looked at product rules, quotient rules, and other rules for partial differentiation. Now this begs the question, what other rules are there for partial derivatives and for their calculation? And in today's video we're going to look at the chain rule for functions of more than one variable. Okay? So the basic idea here is to develop a chain rule that we can apply to help us calculate partial derivatives. All right? Now it's important to understand that for functions of more than one variable, the chain rule takes a more profound form and it's a little bit more complicated. Okay? And because of this complication, something that I strongly recommend is to formulate your chain rule via simple diagrams. Okay? And we'll talk about that as we go along. Okay, so this is the most basic form of the chain rule. Here we have a function of one variable, so we have f of x, and in turn that variable x is a function of two things, r and s. Now if we wanted to calculate either of these derivatives, say dw dr or dw ds, then these are the respective chain rules. Note that we have some ordinary derivative here, dw dx, and we also have some partial derivatives here as well. That's because here f is a function of one variable, right? And x is a function of two variables. Right? So let's have a look at this little diagram for the chain rule here. Firstly, we recognise that f, or indeed w, is a function of one variable. Okay, so my diagram starts off like this. Now, x is a function of two things, r and s. Now, to formulate the chain rule, suppose, for example, I wanted to calculate dw dr. I find all the roads that go from the top to an r. So there's one, and each time I go from letter to letter, I form a derivative. So to calculate dr dw via the chain rule, we would need df dx times dx dr. Okay, so notice there's a w here. It's not a big deal. I actually prefer df here. So df dx times dx dr. All right. Now, what happens if we wanted to calculate dw ds? Well, let's find all the ways to go from the top down to an s. Well, there's one way, and so our chain rule would be df dx times dx ds. Now, again, we've got these curly d's here, partial derivatives, because x is a function of two variables. So it doesn't really make sense to speak of regular ordinary derivatives there. Okay, now, if I have time, I'll come back and prove this at the end. I'll prove the chain rule. All right, so let's look at an example here. Here we have a function of two variables, s and r, and we're asked to calculate dw dr via the chain rule. Now, you may be able to calculate this derivative just without doing any complex calculations at all. Well, that's great. However, if you want to use the chain rule, I'm going to employ the following. I'm going to let x equal s over r, And so W is just tan inverse x. Okay. Now I'm going to formulate my chain rule. So here f is tan inverse, right? And it's a function of x. And x in turn is a function of s and r. All right, so you can think of this x as an intermediate variable. Now the chain rule gives us the following. All right, so to formulate the chain rule for dw dr, it's df dx times dx dr. All right, so let's work out those two derivatives. Okay, df dx is going to be, well, I'm differentiating tan inverse x. So it's 1 on 1 plus x squared. And dx dr, well, I've got to differentiate this partially with respect to r. So it's going to be this. Now, notice here I've got a lot of variables. I've got x, s, and r. What I would like to do is just write that in terms of s and r. So what I do is I back substitute. Here I've got x equal s on r, so I replace x with that, and then rearrange and try to simplify. Okay, now just through a little bit of simplification, this will reduce to the following. So that's my derivative. Okay, so you can see the method. First of all, I introduced this intermediate variable to make things a little simpler. I set up my chain rule diagram, formulated the chain rule, calculated the derivatives, and simplified. Okay, now that's one form of the chain rule. There are lots of other ones. And hopefully, as we go along, you'll be able to see how easy these little diagrams are to use. Okay? So, suppose we have a function of two variables, x and y, and each of those variables is a function of t. So x and y are like the intermediate variables, and they in turn depend on t. All right. Now, the chain rule for this case is the following. All right. Now, to produce this from a little diagram, I have the following. F depends on two things, x and y. And in turn, those x's and y's depend on t. All right, so to formulate the chain rule, to calculate dw dt, I go, okay, how can I get from the top to t's? There's two ways of doing it, going down the left branch or going down the right branch. So it's going to be, as I move from letter to letter, I form a derivative. So it's going to be df dx times dx dt. But remember, there's another branch. So I add that other branch, df dy times dy dt. So that's a good way of remembering the chain rule. All right, so here's an example. If f is given by this function of two variables, and in turn x and y both depend on t in the following way, then use the chain rule to find df dt. Okay, so the first thing I'm going to do is formulate the chain rule. F depends on two things, and those two things depend on t. Right? So the chain rule gives the following. df dt is df dx times dx dt. Plus the other branch, df dy times dy dt. So all we really need to do now is calculate these four derivatives and simplify. So let's do that. So df dx, what's that going to be? Well, we go up here and partially differentiate with respect to x. So it's going to be 2xy plus 3y to the fourth times dx dt. Well, if we differentiate there, I'm just going to get e to the t. Now, we want df dy, so let's differentiate there. We're going to get x squared plus 12xy cubed times dy dt. So we go up here and differentiate with respect to y. Okay, so again, we've got a bit of a mess here. What we would like to do is simplify in some way. And because we're taking the partial derivative with respect to t, we're going to turn these into, this expression here into a function of t. So all I need to do is go back up here and replace x with e to the t, y with sine t in here. Okay, so let's do that, and I'm going to get 2e to the t sine t plus 3 sine to the fourth times e to the t plus e to the 2t plus 12 e to the t sine cube t cos t. All right, now it's a bit messy, and you can probably clean that up if you want to. But something that you may be thinking is going, hang on, I don't need the chain rule there. What I can do is just substitute these things into my original function and differentiate normally with respect to t. And yes, you can do it that way. And I actually think that's a more simpler and more commonsensical way to do it. But you can see here we're asked to use the chain rule. Okay? So let's look at an important example where you can't just use that substitution method. So here's an exercise where you must use the chain rule in this exercise. All right, so here we've got the pressure, temperature, and volume of an ideal gas, and they're related by this equation here. Okay, and we're asked to find dp dt at this particular instance. Okay, so how do we do it? Well, the chain rule is the key here. So let's formulate our chain rule. Now, P depends on two things: T, temperature, and V, volume. Now, temperature and volume, in turn, depend on time. Okay, we can make that conclusion from the presence of these derivatives. Okay, so the chain rule is in the following form. Okay, there's two ways to get from the top to t's. So it's dp d big T times d big T d little t. Oops, that should be a partial. All right. Oh, I'm sorry, that should be an ordinary derivative. Let me start that again. It's going to be dp dt times d big T d little t, and the other branch is similar. Okay, so let's calculate these four derivatives, if we can, and see where that takes us. Okay, so this derivative can be constructed from this relationship. So we're going to get 8.31 over V. And this derivative, again, we go back to here and differentiate. That's going to be minus 8.31 big T over V squared. All right, so what we do now is we go up to these values up here, and we're going to substitute them in to this expression. Okay, so in other words, what we're doing now is we're calculating the rate of change at a particular point in time, the point of interest. So going up here, taking these four things and subbing them in here, we'll get something like the following. Times 0.2. All right, so you can simplify this, and you should get the following simplification. All right, so the pressure is slightly decreasing at that particular point in time. Okay. Here's another form of the chain rule. Okay, things are getting a little bit more complicated now. Here we have a function of two variables, x and y, and in turn, x and y both depend on two variables themselves. Okay, so you can see that this is, it's getting more complicated now. But again, all you need to do is draw a simple diagram. Okay, so f depends on two things, and in turn, x and y depend on two things. So all you do is you work, to calculate dw dr, you just work your way down the r branches, and to calculate dw ds, you work your way down the s branches. Okay, still more generalizations here. F's a function of three things, and each of those depend on one variable. So to set up the chain rule diagram for this, here it is here. Okay, so there's three ways to get to a t, so there's three terms. And again, here's an abstract version of the chain rule. We're getting more complicated now. Again, just draw a little diagram. Okay, so let's look at an application of the chain rule. Well, we're going to look at a special PDE called the Advection Pde. Okay, and you can think of it as a transport mechanism of a substance or a conserved property with a moving fluid. And there's a little example there involving dumping salt in a stream. Okay. Now, this partial differential equation here is known as the Advection Pde. Okay, A is a constant and U is a function of two variables, and it's the unknown function. And we're asked to use the chain rule to show that a solution to this PDE is of the following form, where f is some sort of differentiable function. Okay, so how do we do it? Well, basically we want to show that the derivatives of this expression satisfy equation 6. Okay, now to do that we need to work out these derivatives. And to do that we're going to employ the chain rule. All right, so we calculate these two partials by the chain rule. Okay, so what I'm going to do, I'm going to let x minus at just be denoted by v. All right, So to construct our little chain rule here, we know that f depends on one variable, v, some intermediate variable, and v depends on x and t. Remember, a is a constant here. So, from this little diagram, I can produce the following derivatives. du dx is going to be, what's it going to be? It's going to be df dv times dv dx. Okay, and du dt is going to be df dv times dv dt. All right, but let's, just to save a bit of space, let's calculate these things first. Well, we don't know what f is, so we just got to leave df dv as is. What about dv dx? Well, if v is this, then dv dx is going to be 1, okay? Now, du dt is going to be df dv times dv dt. Okay, so where can that take us? Well, we don't know what we don't know what f is, so we can't really get df dv, but we can get this. Let's go back up to here. What's dv dt going to be with a constant? Well, it's going to be negative a. Okay, so I've got expressions for these two derivatives up here in my Advection Pde. I'm going to take those and form the left-hand side of 6. All right, so it's a du dx plus du dt, and from our calculations, it's going to be, I'll take this and multiply by a, and I'll get something like this. And here, I've got minus a df dv. So you can see these cancel out. And that is actually the right-hand side of our PDE. So the equation holds. Therefore, this form must be a solution to equations, the PDE 6. Okay, well, I did promise that if I had time, I'd go back and prove a simple version of the chain rule. Okay, this very, very simple version of the chain rule. Essentially, what you do here to get these derivatives, right, is to do the following. Let me see if I can fit this in. All right. What you do is you fix a point, say x0, as such. And what we're going to do is show that this derivative at this point x0 has this form, okay? And that's going to be true for any point. Now, by the definition of derivative, with respect to s, okay, we can write the partial derivative evaluated at x0 in this way with respect to s. And what we're going to do now, look here, this is just a function of one variable. Okay, because the t0's, sorry, that should be an s0. The t0's fixed here. Okay, so this is just a function of one variable, s. S equals S naught. All right, so if I replace this function of one variable just with, say, C of S, then I get the following. Now, I can just differentiate that as I would a normal derivative. Okay, so by the chain rule, the regular chain rule for functions of one variable, I have the following. Okay? So now if you look, this is just the partial derivative of x with respect to s, and this is just df dx. Okay, so I end up with the following. Okay, so we have the following chain rule. This equals this times this, and this is true at any point, so it must be true in general. Okay, so that's just a basic proof of the most simple form of the chain rule. But essentially we're mainly concerned with its calculation. So draw a simple diagram, calculate the derivatives, and simplify if you need to at the end. Okay.